In this video, we will discuss some alternative ways that we can differentiate vector fields. Those will be called the curl and divergence of a vector field. And we'll begin by first recalling the gradient of f, which we wrote in 3 dimensions as df dx, df dy, and df dz, a vector. So often you will see just the upside down triangle, which we will call del, written as the vector d dx, d dy, and d dz. And then we can think about this vector operator of the x, y, and z derivatives as something that we can apply to different mathematical objects. The first thing that we've already done is we've applied this del to a multivariable function f. So we looked at the gradient of f, which was del, the vector d dx, d dy, and d dz, applied to the function f, which takes in inputs x, y, and z, but only outputs a real number. The result was the vector df dx, df dy, and df dz. But there are other ways that we can combine this del operator with functions. So for example, we could take the dot product of del with a vector field, say capital F. And since del is a vector and f is a vector, then the result will be a scalar. We could also consider del cross f. The idea here is since del is a vector in 3 dimensions and f is a vector in 3 dimensions, then the result will be a vector in 3 dimensions. So I want to examine these two ideas more closely, so I'm going to start with the divergence. The divergence of a differentiable vector field P, Q, and R, and we're thinking about P, Q, and R as being functions of x, y, and z, is the scalar function written as the divergence of f, or del dot f. So it's del dot f. And then what we've done is we've taken our del operator, which we will recall is d dx, d dy, and d dz. And we've taken the dot product with p, q, and r. So that dot product will give us just the derivative of p with respect to x, plus, and then the derivative of q with respect to y, plus the derivative of r with respect to z. And so by taking the dot product of del with f, the result is a scalar function of x, y, and z. So before we get into interpreting this divergence, I want to do just a quick example of how to compute the divergence of a vector field. So for example, if we wanted to do the divergence of the vector field f given by x squared y minus natural log z minus z e to the x plus tangent y and y squared sine z, then what I would do is I would take the x derivative of the first component. In this case, that would just be 2xy. Then I would take the y derivative of the second component and add that. That's going to be the derivative with respect to y of negative z e to the x is 0. So the derivative of tangent y is going to be secant squared y. And then I'll take the z derivative of the third component, which gives us a y squared cosine of z. So you can see the resulting divergence is now a function of x, y, and z. Okay, so we have this way that we can combine this derivative operator del with f using a dot product. We call it the divergence, but what does the divergence mean? Well, the easiest way to interpret that is to think about f, the vector field, as being the velocity of some fluid. Then the divergence measures the tendency of a fluid to diverge from a point x, y, z. So here it's measuring the rate at which the density of that fluid exits a region of space. So let me give you some examples. I'm going to start with the divergence of the vector field f equal to xy. So I'm just going to use a two-dimensional vector field here, and I'm going to find the divergence of that vector field. So in this case, del dot f is going to equal the x derivative of x, which is 1, plus the y derivative of y, which is 1. So it's going to equal 2, and that's going to be a positive divergence. And so what we can see is if we imagine that there's a little bit of fluid in some region in the plane, then if we follow the arrows, which are getting larger as we follow them, then the result will be that the fluid is more spread out. Okay, so the idea here is that the fluid is diverging from this initial point, and then the resulting fluid is just going to be a little bit more spread out, because the vectors you can see are getting from smaller to larger, and that's kind of spreading out. That's spreading out my fluid. So positive divergence for this vector field, which is describing the velocity of the fluid, corresponds to that fluid spreading out. Okay, well, let's look at a similar vector field. Okay, this will be the vector field negative x, negative y. And so here I'm going to have that the divergence of f is the x derivative of negative x, which is negative 1, plus the y derivative of negative y, which is also negative 1. So I get negative 2. So I get this negative divergence. And so here, if I take a section of fluid described by larger arrows, and then I follow that progression, then the result will be that the fluid is now more concentrated in that area. Okay, and that corresponds to a negative divergence. So now what was spread out is going to be more condensed when I have a negative divergence. You can think about the divergence also as being a measure of the tendency of that region to act like a sink or a source of fluid. So here with the positive divergence, we see that the fluid is getting more spread out. It's acting like a source of the fluid. When we have negative divergence, then we see that the fluid is condensing, right? Or we're losing fluid. It seems like that's a sink that where the fluid is being sucked into that sink. So we have that this fluid is more spread out, and then it becomes more condensed there. Okay, I would like to look at one more example. And this example is the vector field y comma negative x. So when I take the divergence of this vector field, then I'm going to do d dx of y, which is 0. And then I'm going to do d dy of negative x, which is also 0. And so I have here 0 divergence. So what that means is that the fluid, if I look at it in maybe a little region of space here, so let's say we look at this fluid here, and then I follow the natural progression along here, then what happens is that the fluid is rotated, okay, but it doesn't really change side. So it's not getting any more spread out. It's just rotating the fluid. So I can imagine that as I continue this progression in this direction, that here it's not even rotating it. It's just moving along, and it's not really changing size. So here the fluid is rotating, right? But the areas are not changing shape because these vectors aren't getting any larger or any smaller as I'm following that progression of fluid. And so because we're not changing the shape there, then it's not getting any more spread out or more condensed. That divergence is going to be 0.